Hello, everyone, and welcome to the Hyperthesis, episode number 87. We are very excited with a special guest today. But before we start, I'm Patrick.
I'm Pheely.
I'm Liam.
And I'm Jean-Marie.
So, as you can hear, we have Jean-Marie joining us today. We will introduce him more in depth for our main topic, but he is currently a PhD student working on dark matter detection at Queen's University. But I don't want to spoil too much. We are very happy to have you here today. Especially a fun fact is that Jean-Marie and I were colleagues working on the same experiment. So for a little bit of background on that experiment, you can go check out an earlier episode. I forget which one, but it will be in the show notes. But we'll be delving a lot more into what Jean-Marie does and some of the exciting events going on in the world of dark matter. Personally, I'm very excited to hear updates about the world of dark matter because I haven't been there for a little while. So
We haven't found it yet.
Darn. You don't have some big secret?
No, sorry.
No. Well, before we get into speaking with you, Jean-Marie, I just want to go through the intro topic today as essentially kind of a state of the art of research in dark matter. It's been a little while since we've talked about it, and I'm sure we will be delving deep into the depths both of the world and of the universe with Jean-Marie. But before then, I just want to provide a bit of background of what's been going on, especially recently with dark matter detection and some very cool instruments that are being used to see what's happening. So, as a lot of you may know, especially if you've listened to that past episode, a lot of dark matter searches are currently going on in Canada at our Sudbury Neutrino Observatory Laboratory in Sudbury, Ontario, decently close to Kingston or Queen's University. But there's quite a number of experiments going on there, all of which kind of look at different ways and different interactions for dark matter.
In one sentence, what is dark matter? As a reminder for some people.
Well, dark matter is, in one sentence,
Or one or two sentences.
Dark matter is most of the matter in the universe, which we can kind of indirectly detect from its gravitational influence on the matter that we can see. But we have not been able to find exactly what dark matter is when we compare what we observe to what we know about the universe and how matter works.
Yeah, exactly. We can tell it's there from gravity, but when you point your telescopes in the sky, you can't actually see it. So that's why they call it dark. Anyway, I just wanted to, we've talked about it before, but I just wanted like a quick reminder in case someone didn't listen to that episode.
Which you should pause right now, go listen to that, and then listen to this one. But with dark matter, there are potential candidate particles that describe it. I think I've gone through the history of dark matter before and how originally observations made people think that they were very massive astronomical bodies that were making up the bulk of this, whether they were dark stars or rogue planets. And that is somewhat true to an extent, but really doesn't explain all of the mass that we're seeing and the gravitational effects that it causes. So the leading theories are that dark matter is some sort of particle, and a lot of these different dark matter detectors are searching for what are known as weakly interacting massive particles. Of course, there are things like axions, which we won't get into, and a few other candidates, but WIMPs are a primary target for dark matter searches because of things which hopefully we'll get into a little bit later. But in order to detect these weakly interacting massive particles, or WIMPs, or at least try to detect them should they exist. We have the very unique facility of SNOLAB, which is about 2 kilometers underground, and it's also under a region known as the Canadian Shield, which is, I believe it's just granite pretty much all the way down. But there's a lot of mining that goes on there. So you have a lot of shielding from cosmic radiation, and you have the opportunity to build a very large state-of-the-art facility 2 kilometers underground to actually host these different detectors. And of course, it was originally commissioned for the detection of neutrinos using the SNO detector, which has now been upgraded to the SNO Plus detector, which I haven't actually heard too many updates with that. But moving back to dark matter itself, and knowing that dark matter is not neutrinos, which we discovered a few years back, there are several interesting experiments going on at SNOLAB. So some of the larger, both physically and in terms of collaboration size, some of the larger ones include the Deep 3600. And again, there are upgrades, and there's always constant work going on to improve these detectors, make them larger, because of course, as they're larger, they have a larger volume that these potential WIMPs could interact with, and of course, changing the ways in which they can tune that interaction. So starting with Deep 3600, it utilizes a large vessel of argon that will detect particle interactions based on the production of light from that interaction. So if I remember correctly, and again, feel free to step in anytime, Jean-Marie, WIMP would come in, interact with the argon, that will produce light, which is known as scintillation, and then that's ultraviolet light that's produced, then goes through this kind of material, which shifts its wavelength. I think it doubles it into something visible, and then it's surrounded by photodetectors, which can detect the light that has been created. And so depending on the energy of the interaction and where it's happening, you can triangulate based on which photodetectors are detecting light and see where this particle was, and also reconstruct the energy based on the amount of light that's produced, or the energy of light that's produced.
I don't know much about light detection, but why would you need to double the wavelength of the UV light to make it visible to detect it? Couldn't you just, is there no UV detectors that you could just put in to detect the UV light?
I know that in many detectors that use scintillation, if the target material can produce a certain wavelength of light by scintillating, it can also absorb the exact same wavelength. So that is the problem. So that's why they need a wavelength shifter, so that it will be more transparent to the light that it has itself produced, and then you can detect.
That makes perfect sense, because yeah, if it has a cross section for emission or absorption, they're kind of like the same thing, right? Yeah.
So that's a very brief one. Maybe we'll get someone from Deep on someday. But moving on from scintillating light to bubbles that are produced. So another very large collaboration is the PICO experiment. And so this uses what's known as a bubble chamber. So that's kind of an older way to actually detect particles. Bubble chambers came not too long after cloud chambers, but they rely on a superheated fluid that's held at a certain pressure. And then as a particle interacts, since it's a superheated fluid, any type of interaction essentially will cause a nucleation, which triggers an event and a bubble to form within the chamber. And so if you're recording this bubble and seeing how it both progresses and how it's formed and how long it takes to return, along with how big it gets, you can kind of work backwards again to determine what the energy of the interaction was. And again, say, okay, is this something that's known, or is this something new like a WIMP? Now, kind of merging those two is a project that I don't think is underground yet, but is still being worked on, and that's the scintillating bubble chamber experiment. So this uses both the scintillation effects, so when a particle such as a WIMP interacts with the medium being used, it will produce both light, but also a bubble. So it's kind of working on two different fronts to detect dark matter. So that way they can use high-speed cameras to try and record the formation of the bubble and even possibly get some directionality from where the particle originated from. So that way we can say, okay, well, this may have come from the direction of the sun or may have came from the direction of somewhere else. Directionality is something that's super cool. But then it's also using that scintillation to also try and examine the energy that's deposited into the medium. Moving on to a completely different type of detector, a solid state detector, is the super CDMS. I forget what CDMS stands for, but this employs some sort of semiconductor, mainly silicon and germanium crystals, that are cooled to extremely low temperatures. And when a dark matter particle actually hits the crystals, since they're at such low temperatures, that small amount of energy that's deposited, I believe, produces a phonon of some sort. And then that can actually be recorded, just because when things are cooled, the atoms within are quite still. And so any addition of energy, even very small amounts, can be recorded quite easily within the semiconductors.
Could you use ultra cold gases? Is that a thing people have done? I don't know.
I mean, the thing is that often when you cool a gas, it turns into a liquid and then a solid. So that is a bit of the problem with that idea.
They don't last for very long, and I guess the time scales that you're interested in would have to be large.
Yeah, even using gases in general is pretty uncommon among these types of experiment because you want the most amount of mass possible. So you want a high density. So when you use gases, you have lower density.
Makes sense.
Yeah. There are other advantages. Well, we'll go there later.
Yeah, I'm an ultra cold gas guy, so I mean, I kind of figure that there's no real advantage to use them, but I just wanted to see if I was missing something.
Yeah, I think a big portion of that is also volume.
Yeah.
Like I remember you shared with us a video of like this super cooled helium vortices, and that was what, maybe a liter or two?
Well, that was a vortex, so I don't know how big you can get. I'm not a superfluid helium guy, but like superfluid helium, I guess, would be the thing to use because it's dense. I guess it's not like a Bose-Einstein condensate. But Bose-Einstein condensates, they're like typically I don't know, like a few millimeters in size, right? And they last for like milliseconds to seconds before they crystallize. So they're not, if you want, like, you know, when I think of particle detection, right, you think of these big tanks of heavy water or these things, argon or whatever, right? And you let them run for a long time and then collect data. It's like the time scales and position scales are way bigger. So it wouldn't make sense, I think.
Absolutely, yeah. And I mean, like, just for using Pico as an example, their goal is to have 500 liter superheated fluid. So that's a lot larger area than like a couple milliliters for a Bose-Einstein condensate or a gas.
So it's kind of opposite.
Yes, yeah. Well, yeah, that one's very much the opposite, but it still uses a fluid of some sort instead of it's, I forget, is Pico, I think, liquid?
Yeah.
Argon? No.
No. I think it's some fluorine composite molecule. I don't remember exactly.
Okay, yeah, yeah, it's something that has a higher density and I guess, more likelihood of an interaction with that. And of course, the larger the volume, the better. Now, of course, there are other candidates for and other experiments. We'll be getting into the NuSG detector, of course, which does use a gas, just not a super cool gas. So we'll be delving into that, I imagine, quite a bit more. But I mean, as Jean-Marie said at the beginning, we still haven't discovered dark matter. It's a field that's still growing, but we're also narrowing the bounds quite a bit. And so those bounds tend to be described by the potential mass of the dark matter particle, and then its cross section. So that just describes how likely it is to interact with other particles. And since dark matter doesn't really interact electromagnetically, which is how we're able to exist and how the bonds in our cells are able to form and everything, since dark matter doesn't interact this way, we're relying on very rare, little occurring events, again, should they exist, and trying to essentially search for something that's much rarer than a needle in a haystack. It's more like searching for a needle. I forget some of the analogies, but it's like searching for like a needle in something the size of the sun or something like that. It's very small odds of finding it. But of course, if you have larger detectors, if you have things that detectors are more sensitive and more able to refine the detections that happen, cancel out background noise, and improve their ability to really understand the energy and the direction of a particle, then you have a lot higher chances of success. And so, that's just a very brief overview of what's going on in dark matter. It didn't barely scratch the surface.
I just found a paper from 2023 on this project that they proposed called Helios, where they use superfluid helium as an ultralight dark matter detector. Hasn't been done, but it was like kind of like a proof of concept paper. So just wanted to throw that out there. That's something I'd be interested in. But yeah,
I mean, I know they have, what's it called? I think it's the HALO, which is the Helium Lead Observatory. And that's used to detect neutrinos. But yeah, I mean, there's so many proposed dark matter
hundreds
detectors
of them,
as well.
I'm sure.
And I mean, this is just at SNOLAB, so a little bit closer to home, but there's stuff going on at CERN too, trying to look at, okay, is dark matter created at all during collisions within the Large Hadron Collider? And then there's, of course, many different underground laboratories. Like,
I think there's even like off-planet satellite experiments people thought about.
Yes. So what we're talking about today and what we'll transition into now is direct detection, whereas looking through satellites and trying to make observations of possible effects of dark matter in astronomy, that's more so indirect detection. But joining us today to speak more about direct detection of dark matter is Jean-Marie. So Jean-Marie is a PhD student under the supervision of Guillaume Giroux at Queen's University, where Jean-Marie also, you did your master's there as well?
Yes, I did my master's there under Guillaume with the same experiment.
Yes, yeah. So you're working on data analysis with the NewsG experiment that searches for WIMPs at SNOLAB and generally light dark matter. We'll see if axions are actually there.
A bit too light for us.
Yeah. But you mostly work on background rejection and is currently working on calculating the new dark matter limits from the SNOLAB data. Of course, the NewsG experiment is now down in SNOLAB. It's been running for a little bit. And also just to say that your PSC is from U de M, and if you couldn't tell by Jean-Marie's name, he is French. Quite so. But we are very happy to have you on today.
Yeah, I'm happy to be here as well. Thank you for the introduction.
So tell us a little bit about what you do for research.
Yes. So I work with the NewsG experiment. I don't know if you said you mentioned that a bit in maybe a previous podcast, but I think it'd be worthwhile. I'll explain it in details. So NewsG, it uses a detector that we call the SPC, or spherical proportional counter. What it is basically is a big ball in metal filled with gas. And we have at the very center, supported by a rod, an electrode, so a nanode, and it has a very high voltage. So when a particle will interact with the gas, so hopefully dark matter, is going through the detector, but then very rarely having some interaction with a particle, an atom or molecule in the gas, it will give it some energy, and then it will recoil. So that if the energy is enough, the recoil will start ionizing some of the gas, and the electrons that are freed will be attracted by the electrode at the center of our detector, or of our spherical detector. So drifting towards the center, once these electrons are very close to the center, the electric field becomes very, very large. So the electrons will start themselves ionizing the gas, and that creates what we call an electron avalanche. And that will make an amplification of the signal that we can then detect as all these ions drift outside of the electrode. It will induce a current that we can detect. And so we can have some measure of the energy of the initial ionization by the number of electrons that were, of primary electrons that were produced. And so, yeah, we'll get a signal that's higher for higher energies. And we can also have an idea of some discrimination. Did it come from the volume close to our central anode, or was it more from the surface? By looking at what we call the rise time. So since these electrons, they will have some diffusion as they drift towards the center, looking at how much time it takes to get from the first to the last electron we detect. If it takes a long time for the signal to rise, we know it's probably a surface event because there was a lot of diffusion going towards the center. Well, if it was the event came close to the center, from the center, then you have a much shorter rise time. There was not a lot of diffusion. So this, with the amplitude of a signal and the rise time, these are ways we can differentiate different types of events. For example, when we're looking at dark matter, we are assuming that it is something that has interacted with our volume because we have a big volume compared to the surface. But a lot of our backgrounds will come from the surface instead because of all the background radioactive things that could be under surface. Of course, we try to have the material in that make our detector as clean as possible, but there's always some little parts that will be not as clean. So, and just the material itself will be very slightly radioactive. So we know that when we look at events coming from the surface, that's mostly background. So using things like rise time, we can differentiate events that we would see that we think, oh no, that's most likely background, to events that come from the volume that are, oh, that is maybe a dark matter candidate. And same with specific energies that we think could be more likely due to backgrounds. So that's what I talk about, like event discrimination or background rejection. That's all of the work I have been doing, is looking at the different signals we have and try to find patterns and see, try to identify what these patterns mean. Do they correspond to a specific background? And then try to find a way to identify this background and remove it so that we can reduce it for a maximum.
So I'm guessing the data that come from these type of experiment is quite like massive, right? Like there must be like constant streams, a lot of data. Like are people storing everything, or is this kind of like a memory system where you pick and choose, or with some kind of algorithm that get rid most of the data that's just not there, or are everything like recorded and analyzed?
Yes. So when I started, I thought, oh my God, we have so much data. But turns out our experiment, compared to other real big data experiments, it's not that much. But we still have some procedures. Basically, it's a trigger system. So if there's nothing happening, then there's no data being saved. But if we have just a trigger system that will see if the signal goes up quickly a certain amount, then it will start recording a little bit before and some a little bit more afterwards, so that we can see the entire signal. And then after it will stop and wait for another trigger. So I don't know how other experiments are. In our case, the rates we have are of the order of 1 a second. So yeah, it ends up not being that much data compared to maybe what you would see at CERN. Right?
Well, when you say not much, like what's the estimate? Is it like in gigabytes you deal with terabytes, or is it like megabytes?
Oh, it's not megabytes. So, of course, it depends as well how you process the data. So, our raw data will be maybe hundreds of gigabytes, and then depends on how long the run is. Of course, we've been taking data for a long time, so clearly way over that. When I talk about hundreds of gigabytes, I'm thinking about in the order of days. But what we do after we get the raw signal is we usually want to process it into some more useful numbers. Like I talked about the amplitude, I talked about the rise times. Usually those are the numbers we care about. And when you have millions of events, you don't want to look at a million signals. It's better to have a million numbers of amplitudes or rise times. So yeah, we'll process some of the runs we think are more useful to look at, and then those will take a lot less space. Although we do keep the full signals stored somewhere just in case, but yeah.
So when you're looking at the amplitude and you're looking at these signals, just raw from the detector, I know there is a lot of calibration that's done with the detector, especially using lasers and whatnot to understand the exact kind of energy that's deposited and the response from that. Can you talk about that a bit more?
Yes, so we have two main calibration systems, which are our laser and argon-37, or in the broader spectrum, just radioactive sources. So I'll talk about this first. So to get an energy calibration, we use radioactive sources. And the point is, when we see a certain amplitude, we want to know how much energy that amplitude corresponds to. Since it's a proportional counter, it's a proportion. If you get twice the amplitude, you expect that it's twice the energy, and it's linear. So we'll use radioactive sources with known energies. But one that is particularly interesting for us is argon-37, because since it's a gas, it will diffuse in the entire volume of our spherical detector. And we only need to put trace amounts, so it doesn't really change the properties of the gas much. But then it gives us an example of volume events, so that it is more similar to what we'll see for dark matter. So it gives us some calibration for that, but also energy calibration. So we can look at some peaks in the argon-37, and this will give us an idea of what energy corresponds to which amplitude. It also can help to have more understanding on the diffusion, since we have a source that's diffusing the entire volume.
Oh, so these type of experiments, I'm guessing are quite sensitive, right? So when you have data and signals, or even the experimental setup, how are you try to get rid of false positives? Are these experiments designed to just detect this exact thing that happened, like, and nothing else would trigger it? Like, how you make sure that is the case?
So this is something that has been difficult for every experiment, not wanting to say, oh, we found dark matter, but then actually, oh, whoops, no, it was just some background we didn't realize. So experiments have been very cautious about what they claim. A lot of experiments, for example, have had rising backgrounds at low energies, but most of them have not couldn't see really how that would be, for example, related to dark matter, and thought it was more likely to just be some unexplained backgrounds. So in most cases, we if we see something we don't understand, the first thing is try to see is there some background we missed. do we think it can correspond to dark matter, or is it something that is a bit too fancy that could be more related to electronics, or maybe it's something that has maybe too much of a high rate, so we don't think dark matter would interact that much. So in these cases, what will happen is that when you don't discover dark matter, which is what basically almost all experiments have been claiming, you do a limit of what dark matter is not. So if you have a lot more background, then your limit will be not as good as what you could have if you had less background.
So, you mentioned the other kind of step of calibration and understanding the energy is using a UV laser too.
Yes. So the laser is not as much for the energy, but what it's more, let's say, monitoring and understanding the electron avalanche. But yes, so as our detector is running, we have a laser that will produce some light, and it goes in optic fiber. And then we have the optic fiber that divides the light into two parts. One will go to a photodetector, so half of the light goes there, and this way we can tag the events. So we don't say, "Oh, we found something." No, it's just the laser events that we use for calibration. And the other half of the light goes to the inner surface of our detector. So it goes inside through the rod, and due to the photoelectric effect, the copper surface will release some electrons, and those will drift and then go and be detected. So this is nice because it gives us an example of surface events, which contrasts well with the argon 37, and that were volume events. But it also helps us, for example, know what is the drift time that electron takes to go from the surface to the center of our detector, just looking at when we tag the event with the photodetector and comparing that to when we see it actually on the electrode. And yeah, we can also change the strength of the laser, and this way we can try, let's say, for do some specific calibration runs where we have very low laser strength, and this way it helps us really understand the electron avalanche, and we can do some modeling with number of electrons, which will depend on the Poisson distribution, something else called the Polya distributions, and this way we can make fits and have a better idea of how the avalanches.
Well, so if this detector works, right? I mean, probably will work, but if it detects the dark matter, like ideally, right? What you were trying to find, like, are you looking for one event, or it has to be like a constant stream of event? Maybe is it one a year? Like, is there any frequency of events you are expecting to be able to say, hey, this is what we find. This is you can be sure that it is dark matter?
So it kind of depends on which cross section you are expecting. So in our case, for lower masses, you expect the limits are not as constrained on cross section. So it will depend also on how much mass and you have in your detector. So I wouldn't be able to give you a number quickly like that. But yeah, as you try to get more and more sensitive detectors, you're expecting more and more dark matter events. Because if you get one event a year, I cannot say for all experiments, but I expect that if they're just a little bit like us, it would be completely missed, because we get way more background than one a year. So it will be completely, basically drowned in the other kind of backgrounds. You do try to do some selection, so that you can see, you can kind of identify it with even if the rate is pretty low. But it's hard to have the confidence to claim a discovery if an experiment sees something strange, often they will say, we've seen something strange, without claiming that they've seen dark matter. And then afterwards they realize, oh, yeah, it was something strange, that was a background. But if multiple experiments see things that kind of agree with each other, then they'll get more and more interested in it. In the case of NewsG, we have the advantage, since we're using a gaseous target. It is extremely easy kind of to change. You just change the gas and then put a new gas. And then if we see things that agree with all of the different gases, that is a pretty good indication that, oh no, we're actually saying something that's real.
So quick comment and question. The comment was, I just want to emphasize the importance of reducing background in the first place. So this is what I worked on for a good part of my master's, was trying to look at how we can remove radon, which is a radioactive gas, from the gas itself. Since it is a gas detector, you will have radon in there, but just trying to limit that amount, mainly because the alpha particles that are released by radon, they are very heavy, they are charged, so they wreak havoc in the detector and essentially oversaturate it, at least from when I was there. So removing radioactive sources and any background materials. There's also this whole process. There's a paper written on it, on how they electroplate the inner surface of the sphere with incredibly pure copper to essentially block any, or try the best to remove and block any radioactive materials in the surface of the sphere. But that being said, there will still be some background, and if it happens at the wrong time, so let's say a WIMP did interact with the detector, but an alpha particle was just released, then you're going to miss that completely. And so, actually, I have two questions now. One, something I never asked, but the UV laser that's used to produce this photoelectric effect, it's pointed in the same place, right? Like it doesn't move.
No. So we try to point it towards the lower half of our detector, just so, because our electrode actually, we have multiple anodes on it, the one we're using currently, so we can differentiate the upper half of the detector and the lower half of the detector. And since the upper half has the rod there, it tends to not be as good as, let's say, stable as the lower half. So we really focus on that one, and that's where we point the laser. The laser, it's not on a specific point. I think it's more of a little bit of an area where the light can go to, but we try to get it to point towards about the same area. At the same time, it's a sphere, so it doesn't change that much.
So with the laser, I'm just curious, is there any worry about ablation of that like thin copper layer that's deposited on from constant exposure to the laser?
I've never heard of that worry. I think since, it's not a specific point that always gets the light on it, it's not as big of a deal. So if I can talk a little bit more about the background rejection, you mentioned, for example, that you worked on, I think, the radon trap. So, we have installed that very recently. Actually, we're trying to see how much it works to reduce the radon. Seems to be, I mean, it's pretty preliminary. Seems to be working well. We'll have like more in-depth analysis. You also mentioned, I think a bit the shielding of the detector. So I don't think I really talked about that, but our detector, it is, like I said, yes, it's a copper sphere, but that is inside a lead sphere, which is inside polyethylene or plastic kind of cube or a cubic shape. And the point of that is to reduce a lot of the background, and that is all underground so that we can reduce the muons. And even our lead is taken from under from like boats that sank in the Mediterranean at the time of the Romans, so that it can be pure lead that has where the kind of small radioactive isotopes of lead have really decayed, so it can be as pure as possible. We use some of that too. So there's a lot of work to do to reject the backgrounds.
Well, I guess I'm gonna move on to more generic questions on the dark matter and all these stuff. So I'm gonna try to stir the pot a bit. So, in your opinion, who with all these dark matter experiments, who got the best shot right now?
uh, it depends on what dark matter is. So, for example, if dark matter is a light WIMP, then some of the best experiments in the world that use, for example, xenon, that have been going to the lowest square section, they will miss it because they're not adapted to that. And then we can find it with our much cheaper experiments. But then I think we mentioned things like axions. Like if it's axions, these experiments are not well suited for that either. So it's hard to say which one is the best one because it really depends on what dark matter is, and that's why all these experiments are kind of needed and are not that much. I mean, some are, but a lot of them are not in competition with each other because they're all looking at different things.
Just as a quick note, I've heard a few people in the field who will definitely remain anonymous, but they kind of said that within the next 10, 15 years, if we don't discover a dark matter particle, then we'll have to start looking somewhere else. Do you have any thoughts on that?
So I see where they're coming from because as detectors have become more and more sensitive, we're coming close to what some have been calling today the neutrino fog, although earlier it was more considered a neutrino floor, where if you go to lower and lower cross section, your detector becomes so sensitive it can detect neutrinos, and this is a background that's basically irreducible. It's impossible to shield against it unless you have half light year of lead or some absurd amount of shielding that is impossible to actually use. So that's why after a certain number of years, once we get there, it's going to be much harder to actually have a good detection for dark matter. But there are ideas on how to get around this. So that's why today we talk more about the neutrino fog. So trying first to have a better idea, a better understanding of the neutrino background, to see how we can make some statistics to understand how much we're supposed to get. But also, we mentioned, I think, at the beginning of this podcast, directionality. So we expect something that we call the dark matter wind, just due to movements in our galaxy. We expect dark matter to come from a certain direction. And so if we see a signal that we can know where it's coming from, and we see that it's coming from there, not coming from the sun, for example, then it's way more likely to be dark matter instead of neutrinos. Right?
So, if we finally find dark matter, so what does it mean for us, like as humans being, like what is the next step, or what is really mean by like, okay, we know dark matter is this, like what can that tell us about the insights of the universe? Would it answer some question like black holes, or some things about galaxy dynamics, or are there things that dark matter would answer apart from like what it is?
So the thing that's really exciting is because we don't really know what it is, we don't know what answers it's going to answer the questions to, and it's possible that it will raise many, many more questions. And so when we look at our understanding of particle physics with the standard model, it is very complete. There are some things that are not really understood, but it's mostly very well understood. And so the fact that there's a particle that we believe is like about if we're only talking about matter, it's more than 3/4 of the universe, and we have no idea what it is. Then it seems like it's really important, and way more than the little bits that we know. So depending on what we'll discover what it is, so often theories about dark matter, of what it could be, they try to find something that we don't understand, and they try to find, oh, maybe it could be solved with this, and that will also make a particle exist, and this particle could be dark matter. So for example, axions, it was I think the strong CP problem that it was solving, and they thought, oh, well, maybe that will also be dark matter. There are other things like sterile neutrinos, which are related to the idea of neutrinos oscillating and having mass, which has been observed, but it isn't really an explanation for that in the Standard Model. So that could explain it and also be a candidate for dark matter. There's been talk about asymmetric dark matter particles that would explain why we are in a universe that's mostly matter and not mostly antimatter. So yeah, that's if dark matter is one of those, then I'll explain one thing, but for sure it's going to raise many other questions and open, a bit of a Pandora's box of other things to look for.
Well, so is it possible that can be all of the above, right? Because if we're saying that like it's 3/4 of the universe, well, maybe it's not one homogeneous thing. Is it like are people looking at the possibility? It's like, well, maybe diameter is like a multiple different type of particles, like a mixture of those, or are we thinking that it's one thing and we try to find what it is?
It could definitely be a mix of different things. The problem is we haven't found any of them, so we're hoping to find one, find one that will answer one of our questions, and then once we have found that one, maybe we'll try to understand it better, and we'll realize, oh, actually, that's not enough. There has to be something else as well, and then maybe we'll get more answers. But yeah.
So shifting the topic a tiny bit because we're starting to get low on time. What got you into physics? Like what in high school or during your bachelor degree or whatever when you were a kid? Like what got you interested in science and particularly physics and particle physics?
So I personally, as far as I can remember, just like being the youngest kid you can imagine, I was passionate by physics and astrophysics, especially in particle physics. So I think my parents say that I was like a 3-year-old. I would watch this TV show talking about the universe and absolutely love it. And yeah, so I was, I think, even when I was in primary school, we're just starting, or in kindergarten, I would say I want to become an astrophysicist. And now I'm doing more like astroparticle physics. But yeah, I always thought it was interesting. I wanted to understand how the universe works. And I always thought that physics, you go into like the deepest, most like fundamental knowledge of the universe. And yeah, I feel like trying to understand the universe is a bit trying to understand ourselves, and it's a search for self-understanding, I guess.
So you weren't freaked, yeah. So you were always just interested in like where everything came from, and I mean I've heard stories like my maybe I shouldn't throw them under the bus, but I won't. Someone I know, their kid, when they were 5, they learned that the sun was going to blow up one day, and they had a little bit of like an existential crisis, right? So I guess that kind of stuff didn't bug you. That like we're this tiny little speck in the universe, and you were just like, oh, that's so cool. Where did it all come from? How did we end up here? Some people get really freaked out by that, I guess.
And you definitely can get freaked out by it. If the sun blowing up, I mean, of course, we have more pressing problems. They're gonna happen first, but we gotta. I cannot imagine that someone doesn't find that awesome. The sun blowing up, that is really cool. So a lot of these things, they're just cool. You just want to understand because it's fun to think about, even though yes, it can give you some existential crisis. But then you think, wow, you look at some of the mysteries in quantum physics or relativity, and you think, wow, how is the universe actually like that? I wanna understand this more. I wanna know, and it's just sometimes some of these things like black holes, it's not something that you will ever really encounter in your everyday life, which is so cool to think about it, to think about how it will interact with if we were able to visit one, for example. And I think that's why you get to see these things in movies or stories, because they also think it's interesting.
What make you decide to go into more like experimental side of things rather than like, do the particle kind of theory part?
So in my case, it's a bit strange because the very experimental things where I've seen someone describe like three types of physicists. They're the ones that are just working on the pen and paper, basically, or doing theoretical physics. Then there are the ones that are really working on the detector itself and then trying to change things and seeing how that affects it. And then what I'm doing is really data analysis. So I don't touch the detector much, only if someone really needs help and I'm the only one available. But most of my work is just done on the computer, analyzing the data. More recently, I've been working on the limits themselves, which is a bit more theoretical. But yeah, I don't like working with the detector itself because I tend to be very clumsy and I get annoyed at things not working the way I want to. But I still I feel like there's a lot of value in experimental physics because it's what actually our universe is like. So, for example, I talked about many theories like axions, sterile neutrinos. None of them have been proven. It's possible that they're very cool, very nice, but has nothing to do with how the universe is. So I feel like this is something that's really great about experimental physics is you get to see, no, that's how the universe actually works. This is what is the really truth of what's happening.
And we've reached this point now too, where like the questions we're trying to answer are so deep, I guess. It's like, why are we matter and not antimatter? That you know, 100 years ago, you'd get two guys making an experiment in their like basement, and they get a Nobel Prize for it. And now you need thousands of people, or maybe not thousands in your case, but you need a lot of people who are all experts in very different subjects. So you're the data analysis expert. Without you, it'd be impossible. But also without the guys making the machines, it'd be impossible. And it's a very collaborative thing now for these deeper questions, I find, and I think that's pretty interesting as well.
Mm-hmm. And you're talking about, in the past it was much easier, but they were probably thinking the exact same way we're thinking today, because especially before quantum physics and relativity was discovered, they thought, we've got it pretty much almost all figured out, except these little few things, and then these few things open up so much more. So and they were probably thinking, at the time before you could be a geographer, an inventor, a physicist, expert in medicine, and today you have to be so specialized. And it's similar to how we see it today, and probably how they'll see it in the future, thinking, oh my God, since we discovered dark matter, there's so much more we didn't know about, and we thought it was like that one thing, but actually it was a lot more. So
we've evolved very much. Like we started with like these Greek philosophers in bathtubs postulating fundamental laws of the universe, and now we've got very sophisticated experiments. And like, yeah, exactly, like if it turned out dark matter was axions, like that would, theoretical physics would just be like blown away, because anything that moves faster than the speed of light now just upends general relativity. So who knows what'll happen?
Are axions moving faster than light?
No, okay. Sorry, I'm thinking of something else then.
No.
Tachyons. That's right. Right. Sorry.
It's that first form.
Those are not getting discovered. That's my guess. Axions.
Yeah, so I don't even know what axions are. Apparently, I got them mixed up with tachyon.
Yeah, it's theirs to dream, right? Like, because now we might have the faster than light technology in a few, I don't know, 100 years, but So to move on a bit, I think this is the burning question that we always ask our guests every time. So you're gonna get hit with one of these. So Jean-Marie, what are your hopes and dreams? What are you looking to do? With your PhD, maybe in life, where you want to be a research scientist who study dark matter, or do you want to pivot to do something else, or you want to maybe go work in some kind of industry that do like instrumentation? Like, what is your, dreams and goals?
Yeah, so as I mentioned, since I've been very little, I've always wanted to do physics, and I always had the idea I want to be a researcher. I want to try to figure out the most like weirdest but deepest questions in the universe. So I definitely want to continue in academia, and that's what I've always wanted to do. As I said, right now I've been doing looking a bit less at let's say the signals and background rejection, and more the mathematical, maybe theoretical side of dark matter. And I think that's interesting. So I do want to, even though I talk so highly of experimental physics, I do want to try to see how these, I don't know, try to look a bit more at that. I like dark matter, but I do think also I want to try to look at different things. I think if you work too much on one single thing, you get a bit of a closed mind, even though you get specialized. But I think it's a good idea to try to spread your wings a little bit and try things that could be related but are a bit different. So that's what I'll be looking for. I don't have something specific in mind yet, but that's what I am thinking. And I hope that I can do research until I die, I guess.
Well, that's that's not a bad plan, right? And the like your emphasis on the specialization on these days is like when people hear the word, we are physicists, we are scientists, I think they expect to be able to answer a lot of questions about science and physics. And that comes with also like years of experience, I guess. When we talk to our supervisors, I think they seem to be able to come off the top of their head like bunch of papers and theories and things that like I never knew before that existed, right? And a lot of time in general media, the science communicators have that skill of like knowing a lot of little things or big things that are around in the field. They might not personally work on like highly detailed or deep understanding on specific things, like what you do when you are in part of as a part of your project or as part of your work. But being able to basically know a bunch of things and off the top of your head, be able to basically impromptu answer these questions, I think are good skills as for scientists. And also if you want to teach, for example, I think it's very useful for that. Well, I think it's about time we kind of move on to our last section. Well, thank you, Jean-Marie, for answering all these burning questions. And I hope the audience get something out of it, learning more about dark matter, whatever it is, or whatever it's gonna be or not gonna be. Well, before we move on into the next part, I'll get Patrick to tell people about us.
Yes, and I also want to thank you, Jean-Marie. It's good to see you again. And just actually a very quick update from the NewsG collaboration is they just pushed one of their newest article to the archive, I think earlier this morning or late yesterday. So you can go check out how ionization works with the NewsG detector when it was over enjoying a vacation in the Alps.
Yeah, and a few months ago, we've also pushed to the archive our new dark matter limits from when the detector was in France at the LSM, and that has been like one of our biggest papers in years, and a lot of years working on it, honestly. So if you are interested, you can look at that one too. Yeah.
And those will both be linked in the show notes. But if you want other links or you want more information about this episode, or you have an interest in a topic that you really want to hear about, or you're an expert in your field, much like Jean-Marie today, then we would love to have you on the show. So you can reach out to us. You can find us through email. We are hyperthesispodcast@gmail.com. You can send us an email with questions, comments, queries, or inquisitions. Trying to figure out new words I can use there. But if you have interest in a topic, or again, you're an expert in your field, send us an email. If you're not so much into email, you're more with the times, you can send us a DM on Instagram. We're at the Hyperthesis. We also provide updates, so we are recording a few episodes in advance, but we'll be updating everyone when we post episodes, when we come back from breaks. It's also spooky, scary season now, so maybe we'll get a spicy science spooky meme or scary action at a distance meme or something like that. I'll leave that to Liam. If if you're listening to us, congratulations, you have found us. But if you'd like to share us or find us again, we are based out of Spotify, but you can find us on pretty much whatever podcasting service you use. We are also on YouTube. We'll see how updating for this season goes, but we are up to date, up to the end of season 6 on YouTube, so you can watch our videos there as well. I was reading recently that they did a survey about, I think it was like Gen Z versus millennials, and there were some people that listed that they have YouTube on just constantly in the background. So put us on in the background and maybe you can learn something. Apparently some Gen Z millennial hybrids too are doing that. And if people want to ask you questions, Jean-Marie, do you have a way that you'd like people to contact you?
I guess probably email. Maybe I'm more millennial than Gen Z, I guess. But yeah, I don't know if you can link it, or if not, like
Yes.
Google me and you'll find it, honestly.
Yeah, there are very few Jean-Marie physicists who work on the NewsG experiment, but we'll also include that in the show notes. So if you have questions, you can either send us an email and we'll forward it to Jean-Marie, or you can email him directly. Either way, reach out to us. We love having guests on the show. We have a couple more exciting guests lined up, but if you're interested, we have many more episodes ahead of us, and we're more than happy to talk about any field of science, especially given our different backgrounds. Today was very physics heavy. Who knows what will be in the future?
Yeah, it's great being here. Thank you. And yeah, if you want to come here as well, it's a lot of fun. So don't hesitate.
Is it possible to get a SNOLAB tour? I've always wanted to go down there.
So
Same.
I think actually they're do tours. I know that I think it's either this weekend or next weekend they have like the friends and family visits.
So once a year, I guess they would do that, right?
Yeah, so I know it became a lot more complicated during COVID, and it stayed complicated after COVID. So I don't exactly know how easy or not it is, but there's definitely have been visits after that. So I don't know if just one person, they can probably just write an email to SNOLAB and ask them, and they'll tell them, because I can tell you it's a really cool visit. The first time I've ever been to SNOLAB, it was really impressive.
Yeah, I can imagine. It's one of these things where I'm not going to worry about it now, but it'd be cool in the future to get like a group of my physics friends together and try and like 10 or 15 of us, and try and organize like a trip there or something. I
hope you like prison showers. I hope you like prison showers.
Oh, I don't know about that, but for SNOLAB, I'd do it.
Well, thank you again, Jean-Marie, and we will end talking about, one of the major driving forces behind the SNOLAB facility itself. So, Liam, take us away.
All right. So, even though SNOLAB is being used for dark matter experiments now, it was originally built for neutrino experiments, like we mentioned. So, a bit unrelated to what we talked about today, but still in the spirit. I'm going to tell you the story of Arthur McDonald, who was he's a Canadian physicist who won the Nobel Prize for kind of, I don't want to say building SNOLAB, but like him and a group of physicists kind of like came together and proposed a neutrino detector, and so I guess SNOLAB is like a small fraction of it is his child or something. I don't quite know the logistics of it. Correct me if I'm wrong, but anyway, it's a story of Arthur McDonald and a bit of neutrino physics. So again, Arthur McDonald, he's a Canadian astrophysicist and the director of the Sudbury Neutrino Observatory collaboration. And he's also, in the past, he's held the Gordon and Patricia Gray Chair in Particle Astrophysics at Queen's University in Kingston, so where Pheely and Jean-Marie are, from 2006 to 2013. In 2015, he was awarded the Nobel Prize in Physics jointly with Japanese physicist Takaaki Kajiti for discovering the oscillations of neutrinos from one flavor, electron, muon, or tau flavor, to another, which proved that these subatomic particles have mass. And just like a little quick recap, neutrinos are these elementary particles that are produced in great numbers from the sun, and they move very, very fast, very close to the speed of light. So fast that it's not really, you can't easily tell in an experiment if they have mass or not. You can't just measure their velocity and say that's less than the speed of light, or at least that's my understanding of it. However, the standard model of particle physics predicts that they do in fact have a very, very small mass, I believe. People wanted to figure this out. However, even though they're produced in such great numbers from the sun, they don't interact very much with anything. Like Jean-Marie said earlier, turns out that if you have like a block of lead that's 1 light year long, so that's like about 10 to the 13 kilometers, which is a very large distance. If you fire a neutrino through that block of lead, I think there's something like a 50% chance that it just passes straight through the lead, completely non-interacting with it. So they kind of just go, they're produced from the sun and all these other places in the universe, and they just kind of pass through everything and very, very, very rarely interact with them. There's billions of neutrinos flying through you right now every second. I don't know the numbers, but there's a lot of them. Yeah, so since the 1960s, there were experiments that hinted that neutrinos could have mass, but neutrino detectors produced on Earth, they always repeatedly saw fewer neutrinos than were expected. And this was because, like I said, neutrinos come in these 3 flavors, these electron, muon, and tau neutrinos. But all these solar neutrino detectors that were previously created, they were only really sensitive to electron neutrinos. So to match the theory to experiment, they were missing where are the other neutrinos? Why can't we find them? Or how do we find them? And it turns out that people realize that if neutrinos oscillate, then according to quantum mechanics, they therefore must have mass. And I remember in a quantum mechanics class I took at one point, we did like a quasi-proof of this, but I don't remember the details. So basically, if you can show that neutrinos oscillate, therefore they have mass, and therefore the standard model is correct. At least that part of it. So back to Dr. McDonald. Fun fact, he was born in 1943 in Sydney, Nova Scotia. So like myself, he's a Nova Scotian, so I always like talking about him.
I'm Nova Scotian. Too.
Are you? Oh, I thought you were.
I was born there.
Well,
we were born in
What?
the same hospital.
No, I wasn't. I was born in Dartmouth. So you're
I was
more.
born in
You're like
Aberdeen.
more New Glasgow than I am, technically. Then.
Oh.
Anyway, sorry, you
Carry
lived
on.
in Alberta, so I just thought you were from there and had family in Nova Scotia. Anyway, Dr. McDonald, main topic. He's Nova Scotian, so I always like talking about him. And during our first year of our undergrad, me and Patrick and Pheely actually got to meet him. He was touring the Nova Scotian universities, which was very nice. So that was like a nice little event for the young aspiring physicists we were. And so Dr. McDonald, he graduated in 1964 with a Bachelor of Science from Dalhousie University in Halifax, Nova Scotia, and a Master in Science from the same university in 1965. Then going to the California Institute of Technology to get his PhD in 1969. After that, he worked as a research officer at the Chalk River Nuclear Laboratories, northwest of Ottawa from 1969 to 1982, and then became a professor in physics at Princeton University from 1982 to 1989. Afterwards, he then went to Queen's University in 1989 and worked there, was a professor there until 2013, where he then retired, and he's a professor, he retired in 2013 and is still at Queen's University now as a retired professor, where he still continues to be active in neutrino and dark matter research at the SNOLAB underground laboratory. He's also a past board member of the Perimeter Institute of Theoretical Physics in Waterloo, which we talk about fairly often. So where did the Nobel Prize come into play? In 1984, McDonald's collaborator, Herb Shen, at the University of California, suggested to use heavy water as a detector for solar neutrinos, since unlike the previous detectors, heavy water could actually be sensitive to two reactions. One for for all neutrino flavors, and the other one was sensitive to electron neutrinos, which was, the one that was typically easier to detect in the existing experiments at the time. So therefore, heavy water detector for neutrinos could measure the neutrino oscillations directly. So McDonald, Chen, and some other physicists, George Ewan, David Sinclair, and more, formed the original Sudbury Neutrino Observatory, the SNO collaboration, to exploit this idea in 1984. And in August 2001, the Sudbury Neutrino Observatory, led by McDonald, since 1989, reported observations that directly suggested electron neutrinos from the sun were oscillating into muon and tau neutrinos, thus proving that neutrinos had mass in agreement with the Standard Model. And that's where they won their Nobel Prize. One more fun fact about Art McDonald is that in the spring of 2020, during the COVID-19 pandemic, McDonald helped actually lead a project to mass produce mechanical ventilators at low cost to filter out the COVID virus, because him and his colleagues noticed there were a lot of similarities between kind of the ventilators they used in dark matter experiments, probably in SNOLAB. I imagine there's a lot of ventilation down there to keep things from getting on the experiments and getting in people's lungs. They noticed the difference between those ventilators and the ventilators they use to filter out viruses in kind of medical applications. So not only did he do neutrino physics, he also did medical physics in some sense, which is kind of an interesting combination of things to work on in your life. So that's Art McDonald. Just mostly a few fun facts about him, but kind of like some background on how he got his Nobel Prize and where he's from.
I can talk. I think you talked about how they realized that neutrinos were indeed oscillating. I think that was like really impressive, great discovery, because I think this was not in agreement with the Standard Model. The Standard Model predicted that neutrinos had no mass. So yeah, it's always cool when you realize, oh, you were wrong about something, because then it gives like a lot more ideas of, oh, why was that wrong, and what could that mean?
I thought they had to have mass in the Standard Model. I mean, I don't know what I'm talking about, so you're correct here. I'm not, but I thought that was like part of the. Everyone always says the Standard Model is very good, but like every time I look at it, I feel like there's so many holes in it. Like I thought neutrinos was one of these ones that was like, oh, that's good evidence for the Standard Model, that they have mass, because when you do like nuclear fusion, right, neutrinos are a byproduct, and to conserve things they have to have mass, or maybe there's other numbers that need to be conserved.
They only need to have momentum for most stuff, so they do have momentum, but in most cases, their mass actually is unknown. It's so small that it has never been measured, so we only have some limits of what it is under. But yeah, so in most practical cases, you can assume that it's no mass. In the Standard Model, it kind of also predicts that. It's something has to do with like some parity, left-handed and right-handed neutrinos. So turns out they're all left-handed, and because of that, like some math predicts that actually they wouldn't have any mass. But then the oscillation, it's related with neutrinos being having, of course, the flavor states, which are electron, muon, and tau, and you talked about, but also having mass states that do not correspond. So then when the neutrinos travel, then you have this mixing where maybe you're very likely to have a certain, like, for how fast they went, which would depend on the mass. It will also affect which flavor you are gonna measure. So yeah, that's where the oscillation comes from, and that can only happen if they have different mass states. And if they have different mass states, that means they have mass. And yeah, that's how we figure that
That's
out.
pretty cool. I was slightly misled by the internet, I guess, which maybe I should be more careful with it. Okay, that's interesting that, standard model predicted neutrinos have no mass, and we found the opposite. So why do we like the standard? There's so many holes in it. Why do people keep swearing by it? I don't know.
I mean, we always talk about the holes because that's what's more interesting. We're not going to talk if you've been to Atlas or CMS talk in a conference, they show the standard model predicts this number to be, let's say, 0, and then we've proven that it's like within 0 to like a 10th of a percent or a thousandth of a percent. But we are going to search to be really sure it's 0. So, but that's not going to make the news. So yeah, we're always talking about what's interesting. It's interesting when it doesn't work, when we don't understand. But in most cases, I mean, I find it a bit boring, but it is all exactly as planned as we thought.
All right. Well, thank you for that clarification.
Yeah, no problem.
Okay. Well, thank you again very much for joining us and for providing clarity, both in terms of particle physics in general, as well as the current experiments going on with the NEWS-G and other dark matter experiments and advances. So we were very happy to have you on, and it was nice to see an old colleague. So thank you very much for joining us, and bye, everyone.
Thank you, and goodbye.
Take care.
See ya.